This is Jonathan Ellis, a student at TTU in the Signals and Systems class, and this is a systems question for the final exam. Suppose we model the Stanford clock bell tower as a system, where the hammer to hit the bell is the input, the bell is the system, and the ringing sound is the output. Is the system linear? Approximately. And is the system time invariant? It's reasonable to consider that the system is linear. If we hit the bell with two hammers, adding the inputs, then the sound will mix additively. If we hit the bell twice as hard, for example, the sound will be approximately twice as loud. It might be interesting to find out how realistic this is. Likewise, it's reasonable to consider that the system is time invariant, since if we hit it later, we just get the sound later, though the shifted sound might be mixing with the faded sound from the earlier hammer blow. Is this system stable? Recall that stable means bounded inputs result in bounded outputs. Stability means that the bounded input will result in a bounded output. This system is stable because the output cannot be unbounded. The ringing sound will never be infinitely loud. Give an analytical expression that might represent the impulse response, h of t, of the system. Justify your answer. We can consider the impulse response as the output due to an input. Imagine hitting the bell with a hammer for a very short period of time. The impulse response must be 0 for t less than 0 because the bell cannot produce sound without some kind of input. This indicates the need to use the step function. Secondly, because the sound is ringing and oscillatory, we know that the impulse response should include a sinusoid term of some frequency. Lastly, the ringing sound is decaying. The bell will not continue to make sound forever, and the sound is in fact dying away. Thus we will need to multiply our impulse response with a decaying exponential term. The impulse response should look something like this. H of t equals e raised to the negative at times sine of ft, where a is greater than 0. And that concludes this.